In this video, I would like to talk about the conversion between different linear time invariant dynamic system representations, such as ordinary differential equations, transfer functions, and state space representation. Let's start with the easy one, how we can transform from an ODE representation to transfer function, and similarly how we can transform a transfer function representation into ordinary differential equation form, which is very trivial. Okay, so let's assume that we have a general nth order differential equation. Okay, this is n plus a n minus 1 y to the power n minus 1. It goes like this: a1 y prime plus a0 y, and it is equal to, we have a similar representation for the input dynamics, bn u to the power n plus, it goes like this, b1 u prime plus b0 u. Okay, so what we do is, in order to convert the transfer function, we take the Laplace transform of both sides. In that respect, what we obtain is s to the power n y of s plus a n minus 1 s to the power n minus 1 y to s, and it goes like this. Okay, so if we technically keep track of this, it's fairly easy to see that transfer function of a general nth order ordinary differential equation is equal to y of s is equal to u of s, which is equal to bn s to the power n, goes like this, b1 s plus b0. Okay, from this s to the power n, a n minus 1 s to the power n minus 1, goes like this, a1 s plus a0. Okay, so similarly, it's also very easy to convert from transfer function to ordinary differential equation. The only thing that you need to do is multiply both sides. Okay, so y of s with the denominator, u of s with the numerator, and we know that s to the power n times y of s is equal to y to the power, the derivative of y, nth order derivative of y. Okay, similarly, for example, a1 s times y of s is in time domain, it is equal to a1 times y dot. Okay, so as you can see with the simple illustration, conversion from transfer function to ordinary differential equation is straightforward and very easy. Okay, now let's talk about how we can make a conversion between state space representation and transfer function or ordinary differential equation, especially for a general state space representation or general differential equation. We slightly talked about this in a previous example. When we have a specific case, it was relatively easy to convert a transfer function or ordinary differential equation in the state space form. Okay, so let's remember a state space form. Okay, so we have state variable, okay, which is an element of Rn. Okay, that's great. Y of t is an element of R. We assume it's single input, single output. U of t is an element of R. Okay, so in that respect, we have x of dot is equal to ax plus bu, and similarly, y is equal to cx plus du. Okay, so the goal is converting the state space form into a transfer function form. Okay, and then we can easily convert it to ODE form. Okay, so the good thing is, even if we have a matrix representation, because of the linearity of Laplace transform, we can take the Laplace transform of vectors. Okay, it's very easy. So we will take the Laplace transform of state evolution equation, which is exactly the same, s times x of s, and again we assume that initial conditions are equal to 0 since we are trying to find a transfer function. Okay, it's equal to a times x of s, that's great, plus b times u of s. Okay, so let's try to find first x, and then we will try to find the transfer function. Okay, s times x of s minus a times x of s is equal to b times u of s. Okay, so let's take the x of s parentheses. Okay, so what we need to do is s times I. Okay, so you shouldn't forget I, because si minus a. Now we have a matrix difference. If you just write s, it will be wrong. X of s is equal to b times u of s. Okay, so this is a symbolic variable. Okay, so S is a general complex valued variable. Okay, it can be anything. So since it's symbolic, we don't need to deal with like invertible of this matrix, because we know that there exists S which is invertible. Okay, in that respect, if we technically want to compute x of S, which is equal to Si minus A inverse times B times U of S. As you can see, it's very easy. Okay, now what we need to do is we need to compute Y of S. Okay, so let's remember this. Okay, Y of S is equal to C times X of S plus D times U of S. Okay, so if we compute Y of S, it will be simply equal to C times Si minus A inverse times B plus D, okay, times U of S. Okay, where is the transfer function? This is our transfer function. Okay, so if you know C, A, and B, it is a straightforward computation. Of course, if order of the system is high, taking this inverse can be tricky by hand, but if you are using computational tools such as MATLAB and Python, it's generally fairly easy to do in a computational environment, especially that are capable of using symbol computations. Okay, that's all. As you can see, conversion from state space to transfer function is somewhat straightforward. It may be computational challenging, but it is straightforward. Okay, now let's talk about how we can do the inverse, such as like ODE, or we have a transfer function which is similar to state space. Okay, the problem is, for a given dynamical system, linear time invariant, we have a unique ODE and unique transfer function. But we don't have a unique state space representation. There are infinitely many representations. So there's no one correct answer, but there are some canonical answers. So what are canonical answers? The format of the state space fits into a standard or a general, maybe important form. Okay, if they fit in that form, we call them a canonical representation. Okay, and I will show two canonical representations for now, and I will talk about this later at the end of the class. But it's always to talk about something early on, then refer it again when the class evolves in a more advanced and different framework. Okay, so let's start from a representation transfer function, and for the sake of simplicity, I'm just limiting to a third order transfer function. But if you understand the technique, going over to higher order or lower order is super easy. Okay, so let's assume that we have a third order transfer function. Okay, S2 plus B1S plus B0. I can even go for second order, S3 plus A2 S square plus A1S plus A0 U of S. Okay, so this is a transfer function. I can also use OD form, but for this first form, transfer function is much easier. Okay, so what we do is, we will use the fact that okay, so what are we going to do is, I will technically decompose this into two parts. First one is just the denominator. Okay, so B3S cubed plus, okay, B2S squared plus B1S plus B0 times 1 over denominator, okay, S cubed plus A2S squared plus A1S plus A0 times U of S. And even if we cannot do it physically, from a pure mathematical point of view, what I can do is I can assume that this is a transfer function, okay, G1 of S, and this is another transfer function, G2 of S. Okay, so it's a linear system. I can always compare that. So in that regard, U of S times G1 of S is a different variable. Let's call it H of S. Okay, this is H of S, and H of S times G2 of S is Y of S. Okay, So in that respect, what I'm going to do is I will first try to find an state space representation from U to H. Okay, so what is U to H? So let's look at here. H of S is equal to 1 over S cubed plus A2S squared plus A1S plus A0 times U of S. Right, that's easy. Okay. So what I'm going to do is I will find an ordinary differential equation. Okay, so if I do that, it's fairly easy to see that H triple dot plus A2 H double dot plus A1 H dot plus A0 H plus U is equal, not plus U, okay, of course, so let's clean that. Okay, it is equal to U of t. Right now we have a differential equation, and if you remember from the previous lecture, since U of t is a simple input, just a constant, it's 1, we can use a form of state space definition, which gives us a straightforward representation. In that respect, what I do is my states are x is equal to h dot, h double dot. Okay, so these are my states. Let's assume, let's try if we can find a state representation from this. Okay, what is x1 dot? x1 is equal to h dot is equal to x2. That's great. So what is x2 dot? It is equal to x2 is equal to h dot. Okay, good. Derivative of h dot is h double dot, which is equal to x3. Okay, that's great. Whoop. So what we need is x3 dot. Okay, so x3 dot is equal to h double dot. So how we can find h double dot? We can find from here. Okay, so if I rewrite this, I can see that it is equal to minus, okay, that's great, a2 h double dot minus a1 h dot, that's great, minus a0 h plus u of t. So if I replace h dots with the state definitions, x3 dot is equal to, okay, minus a2. What is h double dot? Oh, it's x3. What is h dot? x3, sorry, this should be 3. x2 minus a0, x1 plus u of t. Now I have my third equation. Now I can finish my state space representation looking at this equation. But this is not the state space representation that I'm trying to find. This is an intermediate state space representation. Okay, good. So if I find the state evolution equation, I can say that x dot is equal to, okay, x1 depends on x2, so it is equal to 0, 1, 0. That's great. x2 depends on x3, 0, 0, 1. Okay, in this representation, this part is very critical. Okay, it always looks like this. Okay, that's great. If I look at the x3 double dot, I can see that. Okay, so this should be, that's great, a minus a0 minus a1 minus a2. That's simple. X plus, so what is b? 0, 0, 1. Okay, I think it's fine. So now what we have is we can have a technical state representation from u to h, because we know that h, since we are looking h, y is equal to, what is h? If you look at this, it should be equal to 1, 0, 0, x plus du. Okay, but instead of y, it is an h. Let's say that h. Okay, good. Now let's try to concentrate on the state transfer function and try to find something from this. Okay, I will clean that because it's not critical, but I will directly use this part. Okay, so we know that x dot is equal to h dot, and h double dot. Okay, now let's try to concentrate on the second part. What is y of s? Y of s is equal to g of t times h of s. That's great. What is g? G is this. So if I rewrite this, okay, so y of s is equal to, okay, b3 s cubed plus, okay, b2s squared plus b1s plus b0 times h of s. Okay, so what is s times h? It's h dot. What is s squared? H double dot. Okay, that's great. So y of t is equal to, that's great, b3 h triple dot plus b2 h double dot plus b1 h dot plus b0 h. Okay, that's great. So what I can do is I can write it like this. b3 h double dot. I need to figure out this, but what is h double dot? It's x3. It's true. What is h dot? It is x2. What is h? It is x1. Okay, so we have a problem because we need to figure out what is h double dot. But we know that it is equal to this, right? Okay. Okay, so I can rewrite this like this. b3. Okay. So what is h triple dot? Do we have a simple representation? Okay, now we have that. Okay, so h triple dot is equal to x3 dot, and it is equal to this. So if I copy that, okay, so let's try to be careful. Okay, copy, that's great. So let's paste it here. Paste. Okay, let's keep it here. Okay, so this is technically h triple dot, so I need to just write this. Okay, this is equal to minus a2 x3 minus a1 x2 minus a0 x1. Okay, I think plus u of t. Okay, but we still need to write the other parts, plus b2 x3 plus b1 x2 plus b0 x1. Okay, that's great. Now I don't need that. Okay, so what's this? So let's first look at that. Okay, this is an equation that maps the states input to the output. So what we need to do is we need to convert it into y is equal to cx plus d form. Okay, so it's very easy. So first of all, let's group everything that is similar to each other. Okay, so let's look at x1s. We have an x1 here. We have an x1 here. Okay, so this is equal to b0 minus a0 times b3 x1, right? Because we have b3 here. Plus, now let's look at again. We have x2, we have x2. So if we write this, b1 minus a1 b3 x2. Okay, let's do the same thing to x3. Okay, x3 and x3. Okay, b2 minus a2 b3 x3. The only thing that is left is b3 u of t. Okay, so the form that we want to fit in is this. Y should be equal to cx plus du. Okay, that's great. So it's very easy. So what is c? Okay, we know that x is composed x1, x2, x3, so it is equal to b0 minus a0 b3. Okay, b1 minus a1 b3. Okay, b2 minus a2 B3. That's great. This is X. What is D? D is simply equal to B3. Okay, so it's kind of ugly B. So let's make it pretty. B3 times U. So we computed A, B, and we computed C and D. Okay, the good thing is the state evolution equation for the intermediate step is exactly the state evolution equation of the original system. But of course, in order to handle the numerator dynamics, what we do is we only update the output equation. Okay, good. So this is called controllable canonic form. And now I will write A, B, and C D matrices for a general nth order transfer function. Okay, so for a general nth order transfer function, what we do is this. Okay, so let me find that. Okay, good. So in an nth order transfer function, A will be equal to, so zeros here. These are bunch of zeros. Okay, pure zeros. So we have 1, 1, 0, 0, 0, 0. So we have a giant n minus 1 dimensional identity matrix here. Okay, so we have coefficients of the denominator here, A0, okay, to up to minus an minus 1. Okay, this is my A matrix. It's a control canonical form A matrix, which is equal to B 0 to 1. As you can see, this is also very easy. All zeros here, okay, and just 1 here. And in this representation, C matrix is simply equal to B0 minus Bn A0. It goes like this until Bn minus 1 minus Bn An minus 1. Okay, that's it. And our D matrix is equal to Bn. Okay, for a transfer function, okay, so we initially find that, okay, for a transfer function in this form, okay, nth order transfer function, one way of finding state space representation is this. Okay, so it is given here, and this is called controllable canonical form. And I will talk about controllable canonical form later at the end of the class again and talk about its meaning. But from this perspective, what is important is you can use this form to convert a transfer function into a state space representation. The other form is called observable canonical form, which is the dual form. I will not go into the derivation of this form in this video. I will just give you the end result. Okay, so let's assume that we have a transfer function in this form again. So let's do that. Let's copy it. Okay, let's copy this part. Okay, copy. That's great. Okay, so we have g of s. So another canonical standard state representation is called observable canonic form, and it has a very similar state space representation, which is slightly different. I will show you that. So I have zeros here. Okay, these are all zeros. Okay, now I have an identity matrix, but it is located in this part. Okay, this is zeros, this is zeros. So this is an n-1 dimensional identity matrix. That's great. And the coefficients are not in the bottom row, it's in the rightmost column. Okay, and I locate the coefficients from A0. Okay, so let's make it different. Minus A0 to minus An minus 1. Okay, this is the A matrix. B matrix is equal to B0 minus Bn A0. It goes like this. Bn minus 1 minus Bn An minus 1. We have a B matrix. So C matrix is very similar, okay, to 1. Okay, so we have zeros, and D is equal to Bn. Okay, so actually this A matrix is the transpose of this A matrix. This B vector is the transpose of the this symmetric vector, and this vector is the transpose of this E vector. So these are the dual forms, and they are directly connected to each other. One of them is called controllable canonic form, the other one is called observable canonic form. Okay, so at this point of the class, what you need to know is this. Given a transfer function, you can convert it into a state space form using these standard representations. But you should always keep in mind that there exist infinitely many different representations. You can use different techniques, some intuitions, come up with different representations. But the importance of this representation is, first of all, the format is given. Conversion is easy if you know the derivation, of course. And you can simply use these formulas to convert the transfer function into state space form.